Hello everybody. What I'm going to do today is a review of the gas laws that you were taught. What we're going to do is we're going to first start off with Boyles Law. Now, as you know, gas laws are mathematical relationships between volume, temperature, pressure, and the quantity of a gas, which is measured in moles. So when you are reading a question and you want to find out what equation to use, you'll notice that most of these laws have a constant. In Boyles Law, the constant is the temperature. And in this law, the relationship is inverse, which means as you increase the pressure, the volume goes down, or vice versa. Okay, think of a balloon. You decrease the volume, the pressure goes up inside the balloon. And the equation that we use for Boyles Law is initial pressure times initial volume is equal to final pressure times final volume. Notice, since temperature is constant, it is not part of the formula. Okay? So this is Boyles Law. Now, when we get to Charles' Law, notice that the constant here is going to be pressure. Here, the relationship is between temperature and volume, and it's a directly proportional relationship. As you increase the temperature, the molecules start to move quicker, but what happens to the container as a result is it expands. And that's how the pressure is kept constant, by allowing the container to expand. Now, mathematically, the relationship is expressed like this. The initial volume divided by the initial temperature is equal to the final volume divided by the final temperature. Notice that pressure, because it's constant, it is not part of the equation. Now, one other thing to note, you must remember that the temperatures must be in Kelvin. So, if they give you a temperature in Celsius, before you do the math, add 273 and change it to Kelvin, and then input it into the formula in order to do the math. All right, next one, Gay-Lussac's law is a relationship between temperature and pressure. This time, volume is constant. So imagine you have a container and you're increasing the temperature, which causes the molecules to move faster. And all of a sudden, the container cannot expand. It's at constant volume. What's going to happen is, if the container cannot expand, those particles are going to start colliding more often and with more momentum. So what happens is, as the temperature goes up, the number of collisions increases, which ends up meaning that the pressure goes up as well. Now, there is a mathematical formula. It's also directly proportional. And the mathematical formula looks like this. The initial pressure over the initial temperature is equal to the final pressure over the final temperature. Again, it must be in Kelvin. In fact, all temperatures, when you're talking about gas laws, must be in the Kelvin scale. Okay? And notice that volume does not appear in the equation because the constant will never appear in the equation. Then we have another relationship. This one is between pressure and moles. Now, believe it or not, this one here does not have an actual name. It doesn't, like the others. One is called Boyles Law, for instance, Charles' Law. This relationship doesn't actually have a name, but the way it works is that if you increase the number of moles, which is represented by the letter N, that the pressure goes up. Think about it. Notice if the container is constant volume and temperature, so imagine a balloon or a tire, something that cannot expand. A balloon would probably not be a good example, but imagine a can and you're pumping air into it, or a tire that is not expanding, that the volume is kept constant. The more air you add, the more collisions are going to occur. And that's what pressure is. Pressure is a measure of collisions. So if I add more moles, due to the increased number of collisions, the pressure will increase. Now, we haven't had any mathematical formulas to show you, but I'm going to show you what it would look like. It would actually look like this as a formula if we had to calculate this. Okay, you would actually perform this function here. Again, notice that volume and temperature are not part of the equation. Notice that's been the theme here. The constant is not part of the equation. Okay? And then this last law, we did have a name. It's called Avogadro's Law. And this one, the temperature and the pressure are both constant. And the relationship here is between the number of moles and the volume. And it's also directly proportional. Okay? Notice that if you have a balloon and you add more air, which is what happens when you increase the number of moles, you're adding more air into a balloon. So imagine you're blowing air into a balloon. What's going to happen is the balloon is going to expand, and that's why the volume goes up. If you remove air from a balloon, the balloon will decrease in volume. And the formula for this looks like this. V1 over N1 equals V2 over N2. Notice again, pressure and temperature are not part of this. Okay? Now I have a little trick I'm going to show you that helps you remember these laws, these different gas laws. And that trick has to do with the combined gas law. This is the formula I gave you for the combined gas law. The only thing that's constant here is the number of moles. Notice that the number of moles does not appear in the equation. Now, when do you know to use this formula? Well, if they give you, notice there are 6 variables. You have 3 over here, 3 initial variables, and you have 3 final variables. Normally, if you're given 5 out of 6, that's how you know that you're using the combined gas law. In fact, a good trick to remember is if you cross multiply these two, which is P1 V1 times T2, and you cross multiply these two over here, they're equal to each other. You could actually set this up like this, and you get rid of fractions, and you make the equation linear. And algebraically, this equation is much easier to work with. For instance, let's say you're looking for the final volume. Algebraically, if you want to isolate V2, all you do is you keep your numerator, and then T1 and P2, you would have to isolate the volume, you would have to divide by T1 and P2 over here. Okay, and that will isolate V2. You could do the same thing if you're looking for the pressure, whether it's P2. It doesn't have to be a final, it could be an initial. So let's say we were looking for, P1 on the left, okay? It would be found like this: T1 P2 over V2 divided by V1 and T2. And that's algebraically, it's much easier to figure out, how to isolate these variables by using this linear relationship here that I showed you. Now, let me show you this trick. This you're going to like. Using the ideal gas law, so we got P1 V1 over T1 is equal to P2 V2 over T2. If you learn this one law, I'm going to show you how you can derive the others, okay? Specifically, Boyles Law, Charles Law, and Gay-Lussac's Law. Think about this. If the constant in Boyles Law, okay, in Boyles Law, the constant is temperature. So that means that if temperature is constant, that means that the value of T1 and the value of T2 are the same. Now, mathematically, they're on opposite sides of an equation. So no matter what the value of T1 is, if it's the same as T2, notice how T1 and T2 would cancel each other out. And if you look at what remains, if T1 and T2 are canceled, guess what? This is the formula that I gave you for Boyles Law. Okay? Interesting how that works. Now, watch what I'm going to do. Let's go over here and let's reset this. Okay? So that was Boyles. Now, think about Charles's law. In Charles's law, okay, let's put over here the variables. And in Charles' law, the constant is pressure. So if pressure is a constant, that means that P1 and P2 are the same. That's what it means by the word constant. So do this in your head. If P1 and P2 are constant, okay, that means that what's left in the formula would be V1 over T1 equals V2 over T2. And if you look at the notes I gave you, this is the formula, okay, for Charles's law. Pretty interesting, right? And then let's do this. Let's reset this again. Let's put these variables back up here. Let's go back to the original. And now let's talk about Gay-Lussac's law, okay? In Gay-Lussac's law, the constant is volume, which means V1 and V2 being a constant, they're the same. So if you were to eliminate V1 and V2 because they're the same, the equation that's left is P1 over T1 equals P2 over T2, and that right there is Gay-Lussac's law. So as you can see, by learning the original gas law, the combined gas law over here, okay, you can actually derive Boyles, Charles, and Gay-Lussac's from that one equation. Now, I will show you one other thing. There is another version of the ideal gas, I'm sorry, not the ideal gas law, the combined gas law. And it looks like this. You probably might have seen this, but there is a version that works like this. This is probably a kind of like a universal kind of combined gas law, where you have all the variables that we've mentioned together here, no constants. And I'm going to use this one for a moment so you could see how we can get Avogadro's law. If you recall, in Avogadro's law, there's two constants, okay? The moles, which is the amount of gas is measured in moles. That's our symbol N, okay? And the volume, these are the two things that are being measured, okay? The two constants in Avogadro's is pressure and temperature. Those are your constants. So, based on what I told you earlier, if you eliminate the constants, because P1 will be equal to P2, and T1 will be equal to T2, and you write what is left, you're going to get the formula that I showed you for Avogadro's law, which would look like this. So the combined gas law becomes very useful by knowing that one, and then knowing who's the constant in each of the specific gas laws. You can derive these specific equations instead of having to learn all these different equations. Just learn the combined gas law, and then from that one derive the others. Okay? So that will conclude this lesson. That was a little review on the different gas laws.